Welcome students once again into the class of number theory, and in this video, in this lecture, we will continue with continued fractions. In the previous video we have seen what are simple finite continued fractions, what are their basic properties, how to obtain a rational number from a simple finite continued fraction, and how to obtain a simple finite continued fraction from a rational number. So we will continue this chapter here in this video. So next what I'm going to do is that very easy theorem related to the simple finite continued fractions. If a simple continued fraction a naught, definitely finite, a naught, a1, a2 and so on, an is equal to the simple finite continued fraction b naught, b1, b2 and so on, bm, then if two simple finite continued fractions are same, then each of ai's is equal to corresponding bi and n is equal to m also. That means the number of partial quotients in this simple finite continued fraction is same as the number of partial quotients in the second one. So this we are to prove, and the proof is definitely very easy. Let us see how to prove it. So I am going to start proof of this theorem. We are given that a naught, then a naught is definitely the integral part of the rational number represented by this simple finite continued fraction. So a naught, a1, a2, an, this simple continued fraction is given to be equal to b naught, b1, b2 and so on, bm. This is given, and we know that this number can be written as its integral part a naught plus 1 upon the simple finite continued fraction a1, a2, a3 and so on, an is equal to, applying the same procedure on the right hand side, we will get the integral part b naught plus 1 upon the simple finite continued fraction b1, b2, b3 and so on, bm. In these two simple finite continued fractions, now the integral part of this particular simple finite continued fraction is a1 and of that one is b1. But as a whole, on the left hand side the integral part is a naught, and on the right hand side the integral part is b naught. And we know that if two rational numbers are same, their integral parts must coincide. So this means your a naught is equal to b naught. Integral part of the left hand side is equal to the integral part on the right hand side. And now cancelling these two and taking reciprocal on both sides, what we get? We will get and we will have the simple continued fraction a1, a2 and so on, an is same as the simple continued fraction b1, b2, b3 and so on, bm. Applying the same procedure, the same method, the same technique here, the left hand side now will become the integral part a1 plus 1 upon a2. Now the integral part of the remaining simple finite continued fraction will be a2, a3, a4 and so on, an. On the right hand side we will get b1 plus 1 upon finite simple continued fraction b2. Now the integral part is b2, b3, b4 and so on, bm. Once again, the integral part on the left hand side is equal to the integral part on the right hand side. That means a1 is equal to b1. a1 is equal to b1. And now cancelling a1 and b1 both sides and taking reciprocal and continuing the process, we will get a2 is equal to b2, a3 is equal to b3, a4 is equal to b4 and so on. Repeating this process many times, you will get up to, as we are actually to prove that n is also equal to m. On the contrary, suppose if possible that your n is less than m. Suppose if possible. So if possible, let n be less than m. What will happen? You have just proved that a0 is equal to b0, a1 is equal to b1, a2 is equal to b2, and so on up to an minus 1 is equal to bn minus 1. And then you will get an. It's in fact an is an integer. So either you write it as a simple continued fraction, or you can simply write an. An is equal to, on the other side you will get bn plus 1, bn plus 2, and up to bm. One thing is clear, that on the right hand side, the left hand side is an integer, right hand side must also be an integer, and it is possible if and only if its fractional part is 0. And fractional part is 0 if and only if bn plus 1, bn plus 2, bm are 0. They are all 0. And they are all 0 means your n is equal to m. Because otherwise, if n is not equal to m, that means we are taking that n is less than m. Your left hand side will be an integer and right hand side will not be an integer, which is a contradiction. So to make these two sides equal, n must be equal to m, and n is equal to m, as well as your integral part on the left hand side is equal to the integral part on the right hand side. That means an is equal to bn. An is equal to bn, and rest of the numbers bn plus 1, bn plus 2, bm are all 0, and if they are all 0, that means your n is equal to m. So two simple finite continued fractions are equal if and only if their corresponding partial quotients are equal, as well as the number of partial quotients of both the simple finite continued fractions is equal, is same. So this is one of the theorem where we have left the lecture of continued fractions yesterday in the previous video, and now I am taking another theorem from the chapter. The theorem says that every rational number, or you can say every simple finite continued fraction, every simple finite continued fraction represents a rational number. In the previous video we have proved that every rational number can be presented as a simple finite continued fraction. Now we are going on the reverse process. We are going to prove that every simple finite continued fraction represents a rational number. And the proof is once again very easy. Let a0, a1, a2, an be a simple finite continued fraction. I have used the shortcut notation simple finite continued fraction. So let it be a simple finite continued fraction. We have to show that it represents a rational number, and that we will prove by the principles of mathematical induction. If you are having only one term here, if your n is 0, that means this is just a0 is equal to a0. So a0 is an integer, and a0 is an integer means it is a rational number. So no problem, for n is equal to 0, we are having this simple finite continued fraction representing a rational number. For n is equal to 1, if n is equal to 1, what you will have? You will have a0, a1. That means a0 plus 1 upon a1 means a0, a1 plus 1 upon a1, which once again is a rational number. That means we have proved that for n is equal to 0 or 1, the simple finite continued fraction represents a rational number. This is the first step of principles of mathematical induction. And now let every simple finite continued fraction with n partial quotients with n partial quotients or maybe less than n partial quotients represents a rational number. And now we have to move on to the case where the number of partial quotients is more than n, that means n plus 1. So that means this number, because here the number of partial quotients is n plus 1. A1, A2, An, n are here and one more is here, A0. So we are going to take this A0, A1, A2 and so on, An. And we know that it can be written as the integral part A0 plus 1 upon the rest of the simple finite continued fraction A1, A2, A3 and so on, An. Now look at this simple finite continued fraction. How many partial quotients are here? The number of partial quotients here are n. And in the second step we have assumed that every SFCF, simple finite continued fraction, with n partial quotients represents a rational number. So this is a rational number. So let it be P upon Q. Let this be P upon Q. So what you are going to get is that A0 plus 1 upon P by Q, or you can say A0 plus Q upon P, or you can say P A0 plus Q upon P, which once again is a rational number. That means the final step of principles of mathematical induction is complete. We have shown that the result is true for n is equal to 0 or 1. We have assumed that the result is true for n partial quotients, and we have shown that if the number of partial quotients is n plus 1, even then this simple finite continued fraction represents a rational number. So by principles of mathematical induction we have shown that every simple finite continued fraction represents a rational number. So this was another important theorem to understand that simple continued fraction is rational if and only if it is finite, because in the coming lectures we will show that if the simple continued fraction is infinite, then it represents irrational number. We have just shown that for finite it is rational, and we will show in the future video that if the number of partial quotients in the simple continued fraction is infinite, then the number is irrational. Now we are going to define something more about these continued fraction. Consider this simple finite continued fraction A0, A1, A2, A3, A4 and so on up to An. Consider this one. If you take only first partial quotient, you will get A0. That means you can say A0. If you take the first two, you will get A0, A1. That means A0 plus 1 upon A1, or you can say A0, A1 plus 1. If you take the first three, A0, A1, A2, then you will get A0 plus 1 upon A1 plus 1 upon A2 means A0 plus A2 upon A1 A2 plus 1, or you can say A0 A1 A2 plus A0 plus A2 divided by A0 A1 A2 plus 1. Let me check the calculation first, because A2 is LCM, so A1 A2 plus 1, A2 will go into the numerator and then it's okay. So this is, and so on, continuing like this. This one is denoted by C1, this is denoted by C2, this is denoted by C0, and they are called first convergent, second convergent, 0th convergent and so on. So that means Cn, or you can say Ci. Ci means the ith convergent of this simple finite continued fraction is A0, A1, A2 up to Ai only. Up to Ai only, and this number will be called the ith convergent of this simple finite continued fraction. So this is just a definition. we can have some example as well. So let me take one example of convergence. So let it be a number 2, 1, 3, 4, 2, 3. Let this be the number. Then the 0th convergent is 2. The first convergent is 2, 1. That means 2 plus 1 upon 1 means 3. This is the first convergent. The second convergent is 2, 1, 3. That means 2 plus 1 upon 1 plus 1 upon 3 means 2 plus 3 upon 4 is equal to 11 upon 4. This is the second convergent. The third convergent is 2, 1, 3, 4. So it is 2 plus 1 upon 1 plus 1 upon 3 plus 1 upon 4. Simplifying, you will get 2 plus 1 upon 1 plus 4 upon 13, or you can say 2 plus 13 upon 17, or you can say 47 upon 17. This is the third convergent, and so on. You can find the fourth convergent, you can find the fifth convergent, wherever it is possible. Up to which stage it is possible, you can find the ith convergence up to that stage. So these are the kth convergence, ith convergence of a simple finite continued fraction. So this was just a definition. So I have defined kth convergence for simple finite continued fractions. And now there is one more term. If hi, ki are defined as, we are defining some new numbers, hi and ki, some new sequence you can say, and we are going to define it as h0 is equal to a0, comma, h1 is equal to a1 a0 plus 1, and in general your hi is ai, hi minus 1 plus hi minus 2. If your I is greater than or equal to 2, you can define it by using this recursion formula. And for k0, I am going to define k0 as 1. Your k1 is a1, not a0, a1. And your ki is ai, ki minus 1 plus ki minus 2. If your I is greater than or equal to 2. Define two new sequence, in fact you can say hi and ki in this fashion. Then interestingly, your Cn, or you can say your Ci, the ith convergent is nothing but hi upon ki. This is your ith convergent if you define hi and ki in this fashion. And now we will try to prove this theorem, this result. So let us see how to prove it. Again, we will use the principles of mathematical induction. For I to be equal to 1, C1 is equal to H1 upon K1. Your H1 is A0 A1 plus 1 divided by K1 is A1. And this is true. We know that this is true because this is actually A0 plus 1 upon A1, or you can say A0 A1, which is the first convergent. So for I is equal to 1, the result is true. Now, suppose that the result is true for I is equal to M. Let the result be true for I is equal to M. That means if the number of partial quotients is M, we have supposed that the result is true. If the number of partial quotients is M. And now let us see what will happen if the number of partial quotients is M plus 1. your Cm plus 1 will be A0, A1, A2, A3, Am plus 1. Here we have included Am plus 1. One more partial quotient. If the number of partial quotients is just less than 1, if the number of partial quotients is just less than 1, that means M. By the induction step, our theorem will be true. So what I am going to do, I am going to reduce one partial quotient. So this Am plus 1, I am going to write it as Am plus 1 upon Am plus 1, which will give you the same rational number. So this is your Cm plus 1. So it can be written as Am plus 1 upon Am plus 1. This last partial quotient, Hm minus 1 plus Hm minus 2. Actually what I have done, I have written the value of Hm, because now the number of partial quotients have reduced to M from M plus 1. Combining these two, the number of partial quotients is M, and by the induction step it is Hm by Km. So Hm, because of this formula we have used this. AI is the last one, that means Am. Actually what has happened, this is your Hm. So Am, the last Am is Am plus 1 upon Am plus 1, Hm minus 1 plus Hm minus 2 divided by, we have to write Hm upon Km. Km on the same lines, Km will be Am. Am is the mth partial quotient, but the mth partial quotient here is Am plus 1 upon Am plus 1. So you will get Am plus 1 upon Am plus 1 multiplied by Km minus 1 plus Km minus 2 because of this recursion value. So this is your next step, and now let us see what is going to happen. When you will take LCM from the numerator as well as denominator, LCM will be Am plus 1 and will be cancelled out. The rest of the steps will be, you will get Am plus 1, Am plus 1 plus 1, Hm minus 1 plus, this will be multiplied here also, Am plus 1, Hm minus 2, and similarly in the denominator, Am plus 1 plus 1, Hm minus 1, Km minus 1 plus Am plus 1, Km minus 2. Now look that in the first term and in the last term, Am plus 1 is common. So taking Am plus 1 common from this term and this term, Am plus 1 is common, you will get Am Hm minus 1 plus Hm minus 2, and one more term is there, Hm minus 1. Similarly, Am plus 1, Am Km minus 1 plus Km minus 2 plus Km minus 1. So what the result you are going to obtain now? What is the value of this Am Hm minus 1 plus Hm minus 2? Am Hm minus 1 plus Hm minus 2 is Hm. So you are going to get here Am plus 1, Am plus 1. Am is here, so Am is here, so you will get Hm plus this term is Hm minus 1 divided by Am plus 1, Km plus Km minus 1. So once again apply the same formula and you will get the numerator now will become Hm plus 1 over Km plus 1. That means your Cm is equal to Hm plus 1 upon Cm plus 1 is equal to Hm plus 1 upon Km plus 1. That means the third step, the final step of the induction is being proved. So we have shown that Cn is equal to Hn upon Kn in all the cases. First we have proved that it is true for n is equal to 1, then we have supposed that it is true for n is equal to m, and then we have proved that it is also true for n is equal to m plus 1. That means the result is true in general for every natural number n. So in general, Cn is equal to Hn upon Kn. So this was the very important theorem which will be used in future for various results, for various basic questions related to finite simple continued fractions. So we'll continue the chapter in the next video. Till then, thank you once again.